kører vi.
So today I am visiting AMSAT-OZ, and our colleague Alex is helping us with testing our satellite receiver and sender. Well, our radio station, which is here. We've been running receiver tests on it, and we get a signal better than 137 dBm, which should be sufficient for what we want to do. And here we're measuring the spectrum of the transmitter, and we are getting out around 5 dBm, which with those dampers we have in place on the way should correspond to approximately a sending of 40 watts, which corresponds very well with what we're putting into the transmitter. It's getting a little bit warm by now because we are running a long time test, but everything seems to be okay for what we want to use it for, at least for the Earth orbit. Thank you.
So this is our 7-meter parabolic dish that you can see up there, and it's a mesh dish with a hydraulic drive, and up there outside you can see the different feeding elements, which are basically simple antennas to feed the dish.
So it's a normal antenna that's actually feeding in to the dish as a reflector. Is that correctly understood?
The parabolic reflector is used to collect the waves and focus them onto the antenna, so we have a larger area to receive.
So that can be done both in sending and receiving mode?
Both reception and transmission, correct, yeah. So it's basically just to have, because as you send the radio signals, they will go in all directions. So, and if you can see the small antennas, they have the area they cover, which is small. But if we use the parabolic reflector, we collect much more energy and focus it down to the small antennas, just like an optical telescope does with a mirror. So it's just a mirror which collects the radio waves and focuses on the smaller antennas.
It's correct that you measure those things in dB, right? For how much gain you have in an antenna.
Yes, and it's not really a gain because it's not an amplifier, so it's not it doesn't amplify anything. It's a gain compared to an antenna which has no gain or a simple isotropic radiator. So that's why, and so we compare the efficiency compared to an antenna with no gain, so to speak.
And how much can this one go if it's, let's say, in real use?
How much gain?
Yeah.
Well, it depends on the frequency, but it can be, I don't know, it's in order of magnitude 30 dB up and down, depending on which frequency we use it, and we can use it up to about, I don't know, 7 gigahertz, I would think. And the frequency limit is simply because of the mesh grid, which you can see up. It's not a flat surface; it's a mesh, and it has and there are holes in it. And once the wavelength becomes comparably small to the holes in the mesh grid, then they will be scattered instead of reflected. So that's what sets the limit. And the other thing is, of course, that at higher frequencies, the beam width becomes very small. That also depends on the frequency. And when we get up to, let's say, 5 gigahertz, then the beam width will be, I don't know, below 1 degree. And so our pointing accuracy will not be sufficient for that. It has a hydraulic drive, so it's...
But 437 megahertz, which is what we planned for the first test for Euroluna, falls well within the range of what this can do.
That's it works very well there. So.
Alex, many thanks.
You're welcome. Okay, så den yderste, det faktisk den. Nej, det kan ikke fokusere. Euroluna.
Yeah, so now we've got the radio playing together with the TNC and the computer, so that I can send the first signal through the radio and actually hear that we are getting it reception at the other room. So now I'm going to send a package this way, and the transistor will go on, and then we can hear. Let me do it again, so that you can hear it in there. And that means that now the computer, the TNC and the radio can play together, at least for the sending part, which is a great success for today. Thank you.